Hello, greetings, and welcome to our neighborhood. My name is I1 with nothing. Welcome to Mathematica Notebook Untitled number 2. I just wanted to show you, just some of the power and speed of Mathematica. For instance, in this first line, here, let me highlight it like that. I'll hide the output for both. Oops. Okay, so there's two commands here, limit and plot, and this limit is the integral of e to the negative x squared over 2 from negative infinity to z over the root of 2 pi. That's the formula Gauss found for the normal distribution. A lot of people call it the Gaussian distribution because of it. He's the one who first published this in his PhD thesis, I think, which is pretty cool. Now, in fact, it can do not just integrals, if it can. I mean, you cannot do this integral as an elementary function. You have to write it as a series, which does not correspond to an elementary function. And I'll probably edit that out or not. It'll do limits from calculus and symbolically. I think the direction from below is kind of like inherent in it's starting at negative infinity. So this is like a improper integral. Actually, it goes from negative infinity to z, and what that is that's the probability that the variable will land on z or less. This is the or less part. Okay, and the z is the right bound, the upper bound, technically, of the integral, and we want to take the limit of that. Oops, I think I forgot something. I need to say what the variable is. So let me fix that. So I should put z1 here, and then take the limit as z1 approaches z. That's why it didn't come out the way I thought. Okay. Alright. So it came out with this very quickly. It just did that command real fast. I wanted to get back to the suggestion box. Oh no, come back. I killed the suggestion box. I was gonna plot it, now I have to type it out myself. Damn, I just erased it too. Anyway, ERF, let's look that up. This is how easy it is to get to the documentation. That was super easy and fast. So it's the error. Okay, I know it's the error function. What is error function? Oh, that's this. That's the integral I'm trying to calculate. Basically, it's 2 over root pi. That's weird. Why would it be 2 over root pi? Oh, because there's no half up here. Okay, well, whatever. It's pretty close. Anyway, that's why it's not like a simple function. It's close to just ERFZ. So if we plot that just for fun, the percentage sign means the previous output. Oh, so as z goes from -1 to 1. So this is actually a cumulative distribution function. So let's change the whole thing to, instead of the normal distribution centered at 0 with with standard deviation of exactly 1. So switch to IQ mode, so that the mean IQ, let's say, is 100. It's really not 100, but oh, I know I messed up. Ooh, I knew where I messed up in the last one. Okay, I think it'll be right now. That's good. this 2 is in the wrong place. I'm trying to delete it. Alright, so it belongs here under. Oops. It messed me all up. I'm trying to do this. I have to like spread my hands because only one of my control keys works right now. And it's over 2 times the standard deviation squared, which is the variance, and that would be 15 squared. Is that right? So it's right here. I looked online first. That's the exp right here. Okay, the exp. That's the E right here. And we're looking for a formula for the probability density function of the normal distribution. And what we insist is that the total area under this curve equals 1. That means that the probability of landing somewhere is 1. And sigma here is the standard deviation. Sigma squared is the variance. The standard deviation for IQ tests is around 15 or 16. So let's make sure it's right. Mu here is the mean. Oh yeah, the control button only works on one side. Sorry about that. Yeah, this is Gauss's formula, and as it says right here, the mean is mu and the standard deviation is sigma. So what do I have? E to the negative x minus mu. It's the mean for 100, for IQ is 100. Squared, got that. All over 2 sigma squared, yes, that's correct. And then it's multiplied out front. 1 over the square root of 2 pi times the variance. Variance is 225 for IQ test. And so it's 2 pi times the standard deviation squared, which is 225, I think. Is that right? 2 pi sigma squared, yeah, okay. Sigma equals, well, we could do this too. This is kind of cool. Let's go expand our horizon slightly. Let's get mu up here and see that's 100. Sigma equals 15. That's the standard deviation. That's a rough idea. It relates to the average difference that a result is from the average result. So you're repeatedly rolling a die or repeatedly measuring the same thing over and over and over. So you can develop like a normal distribution of lengths of something. You know, if you really want to be really precise, you might measure it over and over and get a distribution going, and then determine from that using p-values like hypothesis testing, that kind of thing. Anyway, and I think that's all I needed to apply. So this 100 is going to be changed to mu, and then see, it's blue because it's currently unknown to Mathematica. I haven't declared it yet. And then 15 will be sigma. And I kind of did overkill here, but oh yeah, and then 15 should be replaced by sigma. It's easy to type Greek from Mathematica. You type escape, the letter, and escape, like this. Escape, the letter, and you can even, there's a drop box if you don't move quickly enough. You could basically get anything you could think of. There's probably hundreds of, you know, total results, and then escape again and it turns to the Greek version. That's pretty close to perfect, if not perfect. That's what it is. Why is it still giving me? Oh, yeah. Okay. Right. So, that's what it says it is. So according to it, the cumulative distribution function, we're looking at what's the probability or area under the curve that will, the chances that, or yeah, what is the probability that the result will be either at a value or less. And anyway, the ERF function basically is related to cumulative distribution and normal functions. I'm not quite sure how. And then we can plot this. This is kind of weird. Yeah, I should plot it. That's why it looks weird, because there's not much of a bell curve, is there? What is the lowest IQ is possible? 0? 0 means like you answer multiple choice absolutely all wrong, all of them. So that if you had guessed A for all of them, you would have had a higher score. Up to, let's say, 400 as the maximum IQ. Oh no, it broke. Let's do this. Let's paste that in there. This might have more of a chance. Oh wait, no, I want something more like this here. Just because I don't want to graph the cumulative distribution function. It's cool that Mathematica knows that, but that's what I want to graph. And this is not Z1 anymore, it's Z. So this should show a good bell curve. It's thinking too long about this. I don't like it. And if I go numeric, it's not going to know what negative infinity means anymore. How long will it take? I can make it go numerical, but that would spoil it. Let's see what's going on Spotify. That's on repeat. Alright. Thought it was different songs. Shit. I have no idea why that's on my list. Don't know why that's on my list either. I like this song though. And then let's go back to Mathematica land. So this is kind of like how I spend my spare time doing shit like this. I usually don't make a video for it, but this is just the tip of the iceberg for what Mathematica is capable of doing. Like my professor said, that it's dumb, but it's very fast. I've heard that the code behind integrate was like just that command with like 600 pages of code, that very dense code that loosely followed the Riesz algorithm. The Riesz algorithm, one result it can tell you is that the function does not have an elementary antiderivative of any shape or form whatsoever. And it's pretty amazing that can be done. That's called differential Galois theory, I think, which I know nothing about except that. But somehow they prove when certain functions are elementary or not. And so I think what they call elementary is pretty like subjective. You know what I mean? Like, what exactly is elementary? Like, if I put this function composes itself, or I plug like this in for x, it's going to get way more complicated. I have no chance of doing that integral. Okay? And it never learns really. Mathematica doesn't learn. The only way it learns is by getting updates. So I guess when they provide the cognitive reveries, the AI will awaken. So let's see. Let's try to numerically the n integrate. I don't know if it'll look like that. From negative infinity. Probably won't like it. Okay. Let's Cool. I'm not getting a bell curve. Let's try from. Oh, what am I doing? I'm still graphing the CDF, cumulative distribution function. And I want this now to be a variable x. Okay, there's a bell curve. And I'm going to say plot range. You see it? What was the command? I think it's like all. Yeah, okay, so there's our bell curve. As you can see, the mean 100 is represented up here. The peak density output, and I've been told the actual height means nothing really, because things are going on at a like subatomic level, on the infinitesimal level, and that kind of thing, smaller than any kind of known matter, and of any fractional dimension or whatever. He said the height of the PDF probability density function is irrelevant to anything. But what it means is if you take like 1 unit on the, let's say x-axis, horizontal axis, the area under the curve there is roughly equal to the chances that the result will be between that box around that value. That's hard to explain. Wow. Okay, so as you can see, it's pretty monotonous, past like 150 and below 50. So I'm going to switch to 50 to 150. Oops, 50 to 150. And now that's how bell curve looks. Let me try to adjust the aspect ratio so that so it might take it a different shape, a little bit different, yeah. So let me make this smaller. Okay. So as you can see, we have the bell curve. Gauss came up with this formula that generates this curve. He did so without the help of computers, without Mathematica, without shortcuts like having it do integrals for you. It's ridiculous what it can do. It's like, why would you even teach someone for a full semester how to do integrals? Calculus 2 is basically how to do integrals and solve a lot of differential equations. So, with like infinite series also, like how to tell when they're convergent and what they converge to, or if they diverge. Yeah, so mean IQ 100 is represented that the peak value is at 100, and then if you notice here, it's concave downward, and then look at the other extreme values, like below 60 and above 140, it's curving upward. Okay, like it's like it would hold water if it was going to continue. If you continued, I don't know how. I mean, I do know how it's going, but it would just become, an asymptote to the x-axis in both directions. And the total area under the whole curve is exactly 1, and that's what this this adjustment factor, the 2 pi, that ensures the probability will add up to 1, which is the total area under the curve between it and the x-axis, including the fact that it never really touches the x-axis. It still converges, and it's kind of cool. And I wanted to just show how like ridiculous. I made Gauss's PhD thesis look like child's play. I mean, I wonder what he would have accomplished with Mathematica. So I know there's no limits, but it's still sometimes hard to realize that ideal.